Hello, and thank you for joining this webinar. Today we're going to talk about Sindie Best Practices to improve the data quality of your measurements. First, let's talk about the sulfur limits in gasoline. In 2004, sulfur was limited to 120 ppm. And then in 2006, Tier 2 sulfur was capped at 30 ppm average. Now, in 2017, we have Tier 3 sulfur, and the annual average has dropped down to 10 ppm. With these lowering sulfur levels, this has led to an increased emphasis on data quality. And why is this important? It's because sulfur removal costs refiners millions per year in capital, hydrogen, catalyst, energy, and octane. And if you can reduce the variability in your sulfur measurements, you can improve the data quality, allowing the refiner to manufacture the product closer to the specification max, thus saving money. Today's presentation, we're going to go over the following things. We're going to talk about picking the right sulfur analyzer for your needs, using best practices, maintaining your analyzer, calibration tips, and lastly, we'll look at some Tier 3 performance-based measurement system data. But actually, our presentation today is going to focus on these two items that I have outlined, using best practices and calibration tips. One of the things you'll notice during this presentation is that a lot of this is common sense material. You may already be implementing these things in your lab. However, I realize that you are very busy people and you're likely not thinking about your sulfur measurements all the time, so that's why we're going over some of this material. First, let's talk about picking a sulfur solution that meets your needs. I am aware that we have many sulfur analyzers available, and some people have difficulty understanding which sulfur analyzer meets their needs. So you can categorically look at them as good, better, and best. And they're broken into these categories based on limits of detection and precision. So falling into your good category is your Sindie OTG, which has a limit of detection of 0.7 ppm for 900 seconds. In your better category, this is your Gen 2 analyzer. And if you're not sure which analyzer you have, whether it's a Gen 2 or Gen 3, your Gen 2 analyzer is the analyzer that has a standard Chemplex XRF cup. And this analyzer will give you a limit of detection of 0.4 ppm for a 300-second measurement. And this analyzer is available as a 7039 analyzer or 2622 compliant. We also have the best level. That is our Gen 3 analyzer. This analyzer is easily recognized because it uses an AccuCell cup. You'll see that it has a limit of detection of 0.15 ppm for a 300-second measurement. You'll also notice within each of these categories that the precision is slightly better as the detection limit is lowered. Now let's talk about ASTM precision. I'm sure you've seen these definitions before. Basically, reproducibility is your between lab difference, and repeatability is your within a single lab difference. So essentially, reproducibility is where regulation occurs. So that's what we're going to focus on. Also, keep in mind when you're discussing precision, whether we're talking about reproducibility or repeatability, the lower that number is, the better. Here we have a graph of ASTM test method reproducibility for 3 commonly used sulfur methods. There's D2622, which is a wavelength dispersive in green. D5453, which is a UVF method, is in blue. and D7039, which is monochromatic wavelength dispersive, that's in orange. The first thing you'll probably notice is that over a larger range, you'll see that the MWDXRF does have better reproducibility. But then you might take a second look at the graph at the lower end, and you might notice that at the very low levels, less than 10 ppm, that maybe MWDXRF is not as good as WD or UVF. But before you make any decisions there, I want you to keep in mind that this data is based on a single precision study that was made to set up the precision section in each of these ASTM test methods. So it is a single study. So I actually have some data that will tell an additional story about precision. Here we're going to talk about the ASTM proficiency testing programs. Many of you are familiar with these programs because you participate in them. But for those of you who are not familiar with these programs, essentially, a sample is periodically sent out from ASTM, and the participant in this program runs a series of tests. What we're looking at here is the reformulated gasoline program, where a liter of sample is distributed monthly to program participants for a whole series of tests. You'll see at the bottom of the slide, they test sulfur using D2622, D5453, or D7039. The most interesting thing about these studies is that they provide multiple data points over a longer period of time. What do I mean by that? Here, this next slide, I've compiled the sulfur data from the RFG Proficiency Testing Program from 2015 through 2016. Now, I realize there's a lot of information in this graph, so we'll go over it a little bit. First thing I'd like you to notice is the red dots. The red dots are the sample mean for each month that a sample was sent out. You can see the sample mean is on the right side of the graph. And so therefore, if you look at the first set of data points, 1501, that would be January 2015, the sulfur content was approximately 29.4 ppm. Next, you'll see that there are a series of colored bars. These colored bars represent the actual reproducibility by test method for that month sample. So what you're seeing is that in orange, for the sample tested in that particular month, this is the reproducibility for D7039, in green for D2622, and in blue for D5453. Remember, when we're talking about reproducibility or precision in general, that lower is better. So what you can take away from this slide is that over 2 years of data, you'll see that the average reproducibility of D7039 is better than D2622 and D5453. You'll also want to keep in mind, if you own a 2622 analyzer, that this data represents all 2622 analyzers manufactured by all 2622 manufacturers. However, the only analyzer that is compliant with the D7039 precision would be an XOS Sindie analyzer. So for those of you who have a Sindie 2622 analyzer, what you actually get there is D7039 performance with D2622 compliance. Next, we're going to talk about best practices. And here's a summary of what we're going to talk about. Again, a lot of this is common sense. We're going to talk about cleanliness. We're going to talk a lot about canned air and how it can be used to reduce contamination. We're going to talk about preparing samples correctly and using the correct measurement time, checking for sample leaks, preparing a new sample when doing repeat measurements. We'll talk a bit about performing routine analyzer maintenance, and that it's important to calibrate correctly and maintain analyzer calibrations properly. First of all, cleanliness is key. This is obviously common sense. Basically, if you keep your sample area clean, you're less likely to have contamination. You can use a vented hood to help with this. But basically, store materials in sealed containers in a dust-free area. Don't leave pipettes and cups out on an open bench, and promptly cover your sample film after use to prevent contamination. I've given you a couple pictures at the bottom of two potential setups. The setup on the left can lead to contamination, whereas the setup on the right, where everything is covered and kept dust-free, you will avoid contamination. Next, we'll talk about the analyzer itself, starting with the sample chamber. You want to clean the sample chamber with isopropyl alcohol, otherwise known as IPA. This goes a long way to ensure optimal performance. IPA can be used to clean the sample weight or the plunger, as depicted in this photo, which is on the underside of the lid. It can be used to clean the primary window and also to clean the sample basket. What you want to do is wipe the sample weight with a Kim wipe to remove residue whenever it's contaminated. And then you'll also want to clean it with IPA daily or as needed. Next, you'll want to clean the primary window. Now, the primary window I have depicted in the bottom of this slide is 3 different pictures and what it might look like on your analyzer, depending if you have a legacy analyzer, which is the gray analyzer, an OTG analyzer, or our newer M series, which is the orange benchtop analyzer. The primary window is a stainless steel disc with a thin capped-on film. And you'll want to keep this clean for optimal performance. And we actually recommend that you clean it daily, especially if you're regularly measuring samples that are less than 1 ppm. And the first thing you do to clean this is to soak a foam tip swab in reagent-grade IPA. And very importantly, make sure to shake the excess IPA off the swab, because if you have excess alcohol, you actually might leave a residue on your primary window. Next, you'll gently clean the window by keeping the swab parallel to the window and the top surface of the analyzer. You don't want to hold the swab perpendicularly because you may puncture the window. And again, avoid excess force because, again, you can puncture the window. Accidents do happen, so we recommend that you keep a spare primary window. Alternatively, if using a swab is something that seems that it might cause an issue, you can use a wetted Kim wipe or other lint-free cloth. After you're done cleaning the primary window, you'll want to dry the window using canned air. And by canned air, I mean this stuff that you can get from the office supply store that you use to blow out your keyboard. Canned air is great for removing any sort of dust contamination from your primary window, and we'll discuss using it in other areas of our sample preparation as well. But use the canned air to dry off the window. But do note, if you see propellant when you use the canned air, you'll want to repeat the cleaning procedure. Next, we'll talk about the sample basket, and specifically the secondary window. Especially as you're starting to run measurements that are lower and lower sulfur concentration, we actually recommend, for optimal results, that you change your secondary window daily. And to do this, first you remove the sample basket from the analyzer, turn it over, remove the secondary window. This is a good time to clean the metal sample basket with IPA. Then you take your piece of film, Mylar for your Gen 2s and your Gen 3 analyzers, and you're using Proline for OTG analyzers. You'll use canned air to blow off both sides of a piece of film. And then with the sample basket upside down, place the film on the sample basket, and then place the capture ring onto the window film. And it's very important to avoid touching the window film because fingerprints can affect the measurement results. Then the best thing to do is to press the ring firmly using 4 fingers. 4 fingers will help to prevent wrinkles. And lastly, if the window is wrinkled, you'll want to start over, remove the film, and replace it. Now we're getting to where we're preparing samples. Before I start talking about that, let's talk about some basic common sense best laboratory practices. These 2 basic concepts are don't reuse things that shouldn't be reused. Sample cups that are disposable should not be reused. Do not reuse disposable pipettes. Don't wait. Don't prepare samples and then walk away and come back and try to measure it 10, 20, 30 minutes later. You want to analyze your sample as soon as possible after transferring the sample to the measurement cup. And actually, for best results, you want to use a new sample and a new cup each time, even for sample repeats. Because what we've found is that samples measured repeatedly in the same cup will give erratic results over time due to film effects, sample evaporation, and things of that nature. Next, we'll talk about preparing the sample. Use canned air to blow any dust particles out of the inside of the Chemplex sample cup. You're going to find this is especially important with low-level concentrations, such as less than 1 ppm, because these samples are more susceptible to contamination. Of course, if you have a Gen 3 analyzer, you're using AccuCell, so this step will not be necessary. Next, thoroughly swirl the sample bottle before removing it to ensure homogeneity of the sample. Then, use a new disposable transfer pipette to obtain the sample rather than pouring it directly from the bottle. This will help ensure that there isn't contamination. Fill the Chemplex sample cup until the level is about halfway full. You want to make it to be about level with that center cup well. It's actually not necessary to fill the cup all the way up to the top. What you're doing there is you're wasting sample, and you actually this can lead to sample spills and potentially contamination. So you really only need to fill that cup halfway. Of course, if you're using an AccuCell, you're going to fill it with 1 milliliter of sample. You'll assemble your Chemplex cup. Again, with your canned air, gently blow off dust particles from a new Mylar sample film, making sure to always use the same type of film as you used for calibration. You place the film over the sample cup and install the collar. Make sure you inspect the film of the assembled cup. The film should be tight with no wrinkles or swelling, and the sample cup should not leak. So if you look at the bottom of the slide here, you see on the left is a correctly prepared sample cup, and on the right are incorrectly prepared sample cups, which can lead to poor measurement results. Next, we're going to have you use that canned air again to blow off any dust that's on the film. Turn the cup over and place it on a sample stand. Do not place that filled sample cup down, face down on the bench top, because otherwise you've just contaminated the film. Use a sample stand, or if you don't have a sample stand, use a lint-free Kim wipe to put the sample cup down. You're going to vent your sample using a push pin. Make sure you use a new push pin or a clean push pin. We actually recommend that you do 2 vent holes, venting all sample types, and you're going to avoid venting in the center. Now, you'll want to use 2 vent holes, especially for gasoline samples, because as you know, in the wintertime, they will have a high vapor pressure, and you can actually get some vapor lock and bowing of the film. The 2 vent holes will keep the sample film from bowing. And venting in the center is not wrong, but it just leads to more mess on the sample weight. So that's why we recommend that you vent on the edge of the sample cup. Then analyze the sample as soon as possible after preparation. Don't prepare a whole series of Chemplex cups. As they sit there, they can pick up contamination. So we recommend that you prepare a sample, measure it. Prepare a sample, measure it. Next, let's talk about sample measurement. Make sure you're using the correct measurement time. You want your measurement results to meet the precision of the stated method that you're using. So for a Gen 2 and Gen 3 Sindie 7039s and Sindie 2622s, samples that are above 1 ppm, measure for 300 seconds. If you're measuring less than 1 ppm, we actually recommend that you go and do a 600-second measurement. And then finally, if you have an OTG, you're going to want to measure samples for 900 seconds if they're less than 500 ppm, and you're going to do this to consistently meet the D7039 precision. After measurement, remove the sample. Don't let it sit there. If it sits there, there's a potential it could leak in the instrument. And do check the sample for leaks. Check it when you pull it out, because if you have a leak in the analyzer, you could contaminate the next measurement. And obviously, if a leak's detected, clean the analyzer, change the secondary window, check the primary window, and see if that needs to be cleaned. Wipe off the sample weight. And then, lastly, prepare a new sample when doing repeat measurements. Don't measure the same sample twice. Next, let's talk a little bit about analyzer maintenance. Just some simple things to help you get good measurement results. Using best practices, maintain analyzer cleanliness. You'll also want to routinely check the fan filter in the back of the analyzer and clean that off when necessary. That will keep your analyzer from overheating. Of course, you're also going to run SQC checks so that you can maintain statistical quality control of your analyzer. And then you'll recalibrate your analyzer when your SQC chart is out of control. Additionally, you want to perform routine maintenance. For ultimate peace of mind, you may want to consider an XOS service contract. If you'd like more information on that, please contact support@xos.com for more information. Next, let's talk about some calibration tips. I call these do's and don'ts. Do calibrate the analyzer when it's needed. When is that? It's when your control chart is out of range, after major analyzer changes. Some people like to do a periodic calibration, such as yearly. And while this isn't harmful, it may not be necessary. If your analyzer is in statistical control, you don't have to calibrate it. If you do need to calibrate your analyzer, make sure you're starting with a clean analyzer. Clean the primary window. Change the secondary window. Again, we highly recommend the use of canned air here. Next, do use matrix matching or correction factors for the Tier 3 gasoline calibrations to improve your accuracy. As many of you may have found out when doing the performance-based measurement for the Tier 3 EPA testing, gasoline has a small, about a 1% high bias when it's run on mineral oil calibrations. So you'll want to correct for that to improve the accuracy. If you see here, I have table 3. This is pasted from 7039. And here's a correction factor for running gasoline on a mineral oil calibration. Or you can just use gasoline calibration standards. Don't tightly bracket your calibration range. I know that traditional XRF does call for that. We do not recommend that you do not bracket the calibration range tightly. We still recommend that you use a 0 to 500 ppm calibration, even if you're measuring less than 10 ppm gasoline. And why is this? The Sindie uses a weighted calibration. It's extremely linear. And so these high points actually anchor the calibration slope and provides a more stable calibration curve. Do use auto calibration for best results. Auto calibration uses a weighted calibration. It does all the calculations for you. And one thing that's very important is do make sure you have a good calibration blank. If you have a bad blank, you'll have a high calibration offset or intercept, which will lead to bad precision at the lower end. To which you'll next ask, well, what is a good blank? So here, if you look at the table, you can find your analyzer to see how many counts are typical for a 5-minute measurement on your analyzer. Many of you have a Sindie Gen 2 analyzer that uses Chemplex cups, either a 7039 analyzer or 2622 analyzer. And you'll notice that in 2622 mode, your blank will measure lower, and that is because of the background measurement. For your Sindie Gen 3, which uses the AccuCell cups, when you have a 7039 Gen 3, you have less than 200 counts on your blank. However, if you have a Sindie 2622 Gen 3 and it's in 2622 mode, you're looking at less than 100 counts when you measure the blank. And then lastly, here's the information for your Sindie OTG. It only has 7039 mode, so you'll be less than 125 counts typically. Just want to put up a small note here about autosamplers, because all autosamplers use AccuCell cups. So therefore, it may be difficult to remember if that's a Gen 2 analyzer or Gen 3. So if you have a Sindie 2622 autosampler, that's a Gen 2. Use that category. If you have an autosampler that's a 7039, or your autosampler is a 7039 only unit, that's going to be a Generation 3 unit. And speaking of Generation 3 units, we actually recommend that you use a DI water for the blank instead of mineral oil to ensure that the background is very low when you do the calibration. And finally, do read the user manual for more information on how to do a calibration. Next, we're going to look at some advanced calibration tips. Use the stats and replace features on the newer orange M-Series analyzers to improve calibration fit. Now, if you have one of the gray legacy analyzers, I do have a workaround for you. We'll go over this after we talk about the stats button and the replace, but I have a workaround for you. But for those of you with the orange M-Series analyzers, you'll go into your calibration curve screen, and you'll see at the bottom of the screen there is a stats button. So to view the stats of any calibration curve, first select the curve so that it's a current curve, and then press the stats button to view the statistics. What you're looking at here on the stats page, on the left are the standardized residuals of your calibration standards, and on the right is the fit. The standardized residuals should be between -3 and +3, or it'll be removed as an outlier. But actually, if you want a really good calibration, you want to be less than 2 on your residuals, or even better if you can be less than 1 on your residuals. And remember earlier how I said that the Sindie is extremely linear? By extremely linear, I mean 0.9999. If you have 0.98, that's not a good correlation coefficient, not on a Sindie analyzer. It should be very close to 1. We expect that you'll be able to get 3 nines when you calibrate. 4 nines is good, and 5 nines is great. And one of the things you can do is to consider replacing or removing some of the calibration points that have high residuals to improve your fit. Next, before running any of your new samples, you would run a check sample, right, after calibrating. Before you do this, you can actually remove or replace any of the bad points in your calibration. So here you're in the auto calibration page, where you enter your calibration points on the left, and on the right are the counts per second. To remove any of the points that you don't want to use, you press the clear button. This removes all calibration values. Then you re-enter any of the points that you want to use on the left in the ppm fields. Do note that anything that is left as asterisk is not used in the calibration. And we also recommend that you have a 4-point minimum calibration. Don't remove more than 2 calibration points. Next, we're going to talk a little bit about replacing bad calibration points. What you want to do here is to touch the red asterisk to the right of the replace button, and that you enter the number of the point you would like to replace. Make sure you remember that when you look at your points here, they're in reverse order. So the last point that you ran is in position 1, and the first point you ran is in position 6, so you know which one to replace. After you've entered the point that you want to replace, you push the replace number button to exit the calibration screen, then done to return to the ready to measure screen. Next, you will measure that calibration point that you're trying to replace. The counts per second of that next measured result will go to the position that you selected in the auto calibration screen. And then after that, you can return to the auto calibration to finish the calibration, or you can replace other calibration points. Do note that you can only replace 1 point at a time, and you can replace the points as many times as you wish. Then when you're done, finish calibration and go back and check your stats. Now, for those of you who have the legacy analyzers, you don't have access to the stats and the replace buttons. So we have a workaround for you. We have an Excel spreadsheet that does a weighted linear regression. It's called Low Range Calibration Rev-D. It's an Excel spreadsheet, and what you do is on the left-hand side of the screen, you enter your measured values, and on the right-hand side of the screen, this worksheet will calculate the slope, offset, the fit, and your residuals. And so then what you can do is you can see what your residuals are, and you can see what your fit is, and then you can remeasure points and replace them in here as needed. And then when you're done and you like what you see here for a calibration, you then enter this into your Sindie manually. If this is something that interests you, please feel free to email me at ljohnson@xos.com to request a copy of this worksheet. Next, your calibration is finished. The last thing you want to do here is to run a calibration check. This tells you whether your calibration is good or not. I do often get asked, what is an acceptable limit for this check sample? Well, here's some options here. If you already have an existing SQC chart, you have upper and lower control limits, so you already know what your acceptable check sample limits are. However, if you have a new analyzer, you may not have this chart available. So what you can do is you can use a NIST SRM, which will have an acceptability range. Or if you look in the Electronic Code of Federal Regulations, in the section about performance-based measurement testing, they talk about an accuracy SQC, section 40 CFR 80.47, section N, paragraph 1I. Your accuracy check should be less than or equal to 0.75 times the reproducibility of the method. Alternatively, in both 7039 and 2622, they each have a statement about a check sample. In 7039, it says that the determined value shall be in the range defined by the certified concentration plus or minus the repeatability of this test method. In 2622, it states that the differences between two measured values shall be within the repeatability of this test method. Next, let's take a look at some Tier 3 performance-based measurement system data. For those of you that have been through this testing, you're aware that there are two parts to this testing. There is an accuracy piece, and there is a precision piece. First, let's look at the accuracy piece. Basically here what you do, it's a two-part test where you take a sample that is 1 to 10 ppm, you run it 10 times, and the average of that sample shall not differ from the accepted reference value of the standard by more than 0.7 ppm sulfur. You'll see here we ran this standard. The accepted reference value is 9. The difference was 0.43. This passes the accuracy test. Then again, for the second piece of the accuracy testing, you do the same piece of testing with a sample that's between 10 and 20 ppm. And the sample we used here was a 19 ppm sample. That was an average of 19.33, so the difference was 0.33, which passes. Next, you have the precision section, which basically talks about 20 tests over 20 days. So what is the precision of your analyzer over a longer period of time? So you'll see here that we ran over 20 days, we ran a series of 36 measurements, and you take the standard deviation of those 36 of those measurements over 20 days. You take 1.5 times the repeatability of the method divided by 2.77, and your standard deviation has to be less than that value. In this case, it's 0.99, and our standard deviation was 0.36, so we were passing. And you might ask, why am I showing you this data? The reason I'm showing you this data is that if you use these best practices and these common sense things, and you use these tips for calibration, you should have no problem passing this performance-based testing. And lastly, of course, you have to, as a part of the Tier 3 testing, you have to run SQC charts. Here's an example of a precision SQC chart for a gasoline standard. And that actually brings us to the end of the presented material. I know we went through a lot of information, so I will take a few questions as time permits. And do note that if you think of something later and you have a question, please do not hesitate to contact me. Now I'm going to take a moment here. It looks like we have a couple of questions. And I have a question here where it asks, is it better to use one 600-second analysis time or two 300-second analysis times? And of course, you're going to want to make sure you're following whatever method you're using. Okay. If you're doing 2622, you're going to be required to do duplicate measurements for your gasoline samples. So in this case, I would say that the two 300-second measurements. But in a practical manner, the two 300-second measurements or the one 600-second analysis are fairly equivalent. And then I have another question that states, if we are going to measure less than 1 ppm, do we need to use the 0 to 500 ppm calibration, or would it be better to add some points in the range from 0 to 5 ppm? And actually, we still recommend doing the 0 to 500 ppm calibration. The analyzer is very linear, and these high points will actually help and make a more stable calibration, even for samples less than 1 ppm. And let me see here if there's any additional questions. Let me throw one out here that I actually commonly get after doing this presentation. Many of you have heard about our new Sindie plus chlorine analyzer. You may have gotten some emails or you may have seen us at ASTM. And I commonly get asked is, so where does this Sindie analyzer fall in this good, better, best scenario. So let me go back to that slide. And here you have the good, better, and best. The Sindie plus chlorine analyzer actually falls into the better solution. It is a Gen 2 analyzer, essentially, and so it has a limit of detection of 0.4 ppm with at 10 ppm, a reproducibility of 1.4 ppm. Let me take a moment here and see if we have any additional questions. And I do see that there are actually some questions that will probably require me to do a little research and get back to you. So do note that if you did type in a question today, I will get back to you within a couple days. Some of them look like they require me to do a little bit of research. One of the questions here is there any difference between vacuum mode and helium mode regarding the results? And this would be on a Sindie 2622 analyzer because we offer them both in vacuum mode and helium mode. And actually, there should be no difference. We actually don't use a lot of helium. The analyzer is still under a slight vacuum with helium trickling in, and we're not using enough helium that it would make a difference. And let's see, I have another question here. The D7039 test method has a PLOQ of 3 ppm. How should the results be reported that are under that value? And actually, that is up to the user discretion. We have some customers that just report less than 3 ppm. We have some customers, when they get a result that's lower, they use the limit of detection as a reporting limit. So on their Gen 2 analyzer, anything that measures less than 0.4 ppm, they would report as 0.4 ppm. I've seen a couple more questions come in here. Let me see here. What is the difference between using Mylar or Proline on an OTG or other 7039 secondary windows? And the difference here is basically on the film itself and its transmissivity. You'll notice that the OTG is our good solution. You'll notice that the limit of detection is not as good as a Gen 2 or a Gen 3. And we use the Proline secondary window because it is thinner and more X-ray, it's actually not thinner, but it's more X-ray transmissive, so it allows more counts to get through, so it allows better precision. So it's actually just a little bit of a boost to the OTG precision, and that's why we use it. Otherwise, you generally pick a film based on what is compatible with the sample that you're using. Most Sindie analyzers do use Mylar film. And let me see if there's additional questions. And actually, there are a couple of questions that are here, but they will require a bit of research. So do note that I will get back to you. So with that, let me go here to the... We are actually done with our presentation today. Thank you very much for joining me. And again, if you have any questions later, please do not hesitate to contact me. My contact information here is on this slide. So thank you very much for joining this presentation today.